Hi, my name is David Ernesto Troncoso Romero, and I'm going to explain for you the design of FIR Hilbert transforms using a combined frequency response masking frequency transformation approach. This was published 10 years ago in the Midwest Symposium on Circuits and Systems in this reference here. So basically this approach combines two methods to simplify, to make simpler the implementation of Hilbert transforms. So the Hilbert transform is designed with identical simple subfilters that interact with each other through some extra coefficients. This is a frequency transformation using identical subfilters that employ other extra coefficients that are basically, these subfilters are cascaded. So this is frequency transformation. But in this method we are designing the subfilters. Every subfilter is itself a Hilbert transform designed with three different even simpler basic filters. This is frequency response masking. So we are embedding frequency response masking into frequency transformation. That's the combined FRM FT approach. So to complete the design, we need to find three different basic filters, the three different basic filters that compose the subfilter, and also the coefficients used by the subfilters to interact between them. So these coefficients are obtained from a transfer function that we are going to design, which is called P of Z. So this is called a prototype filter. So we are going to design the prototype filter and also the three basic filters that compose the subfilter. That is what we are going to do. So let's keep going. Here. So the subfilter is composed by three different simple filters. This is frequency response masking, and this is the interconnection between these three simple filters, and we call the subfilter G of Z, and this is the equation 2 in the paper, this one here. Now before showing the structure of the overall filter, we are going to define this array here with subfilters. You see the G of Z here, the subfilter that mentioned in the previous slide here, and with this array we form another subfilter. This LG is the length of the subfilter. The length of the subfilter, it means the number of samples in the overall impulse response. So this is H1. This array is H1, a simple array of subfilters. This is equation 12b in the paper. And now with this H1, and with G of Z, we implement, or we construct the overall filter, the overall structure of the filter, which is given here. We see here the subfilter G of Z, which was composed by three little filters, and we see here H1 that contains two of this here. So we see here the coefficients that I mentioned before, these coefficients. So LP here is the length of another Hilbert transform called P of Z, the prototype filter that I mentioned before. So from this the coefficients alpha are derived. So this is the equation of the overall filter. This is equation 12a in the paper, equation 12a. This one here that describes, this equation describes this structure. Okay. So this is the picture of the overall filter. We see that we have in the sub-filter we have basically three uh, little filters, three basic filters here, and they compose the sub-filter, which is here, 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 and this array is H1 here. So basically we are using repeatedly these three sub-filters here and here and here, these three sub-filters, and also we are interconnecting them with these coefficients that come from the filter P of C. We are not implementing P of C, but we are designing it to get these coefficients. So to complete the overall Hilbert transform, we need to design the three different basic filters GB, GA, and GM, and also we need the coefficients. And for these coefficients, we need to design P of C. From this, we will get these coefficients. So let's see. Now the details. More sub-filters to come. To design this four filters, we are going to need some other filters. So let's see. So we'll start with this. This picture represents equation 1 in the paper. This picture represents equation 1, and is basically the specification. We are given a desired specification. This omega L here, and this ripple here. The desired ripple is delta, and the desired cutoff frequency is omega L, little omega. Okay, so with these specifications, we need first to find M. What is M? M is used in one of the basic filters. Sorry for my English. A long time ago that I don't speak too much English. So, okay. This M is needed here in this subfilter GB. We need M. We call this a expanded filter. It means that every delay will be replaced. Every delay Z to -1 will be replaced by M delays. Z to -M. So that filter that replaces every of its delays by M delays is an expanded filter. We call it an expanded filter. So that's what I'm going to refer. So for that reason we need M, and we can compute M easily. We can compute M like this in terms of omega L, which is given as an specification. This is equation 13 in the paper. M must be rounded to the nearest odd integer. So this is easy. After this, we round it to the nearest odd integer, and with that we can express M. It might be like this, or it might be like this. This odd number can be represented as this or as this. So depending on it, we keep going. If the representation of M is in this form, we need to design now a half-band filter, which we call H half-band, HHB. Okay, we have to design that filter, and so if M accomplishes this, fits in that expression, so we use these expressions for omega S and omega P, the cutoff frequencies of that half-band filter. We can compute this right away with omega L, which is the specification of our Hilbert transform, and with M that we already found. So there is no other unknown here. We can compute omega P, and with omega P we can compute omega S. So we can keep going. That's the specification of our half-band filter. But if M fits in this expression, if M can be expressed with this, we change omega p for this and omega s for this. Again, omega L is known, M is known, so we can compute omega p. Okay, but for the ripple here is the same. This ripple here is the same here. We don't need to specify two ripples because it's a half band filter. It is assumed that this ripple is the same that this one. So for that ripple, we use this expression. Delta G is given here and VD is given here. These are equations 11b and 11c in the paper, but we don't know omega L. We will see later in this presentation how to compute it, but for now let us assume that we know it. Okay, let's keep going. So for now, let us assume, this is assumption 1, that we know this. Okay, if we know, we can keep going. So to design the half band filter, we use the ripple as before and the omega p as before. Let us assume, this is assumption 2, that we know a proper length of that filter. We can estimate a length for that filter if we know this too, but we don't know this one. Okay, so that is why we assume that we can estimate a proper length for that filter. Okay, but we can keep going. We can employ in this step, we can employ this reference, this chapter that I wrote in those times also. And the code is in page 456. Okay, in that page is the code. Now we can obtain GB of C. This is the first basic filter in the subfilter, the first one, from HB. We can obtain from this one that we designed using this relation. Here, LHB, this is the length that we assume to know in assumption 2. And this is the equation 3 in the paper. And here what we are doing is basically modulating the filter. This is a polynomial in C to minus 1. C to minus 1, C to minus 2, C to minus 3. This is a polynomial. And every time we see a Z like this, we replace it by J to M, Z to M. That's what we are going to do. Every time we find a Z, we replace it by J to M, Z to M. Okay. And that's what we are going to do. And this, even though we are using J is the root of minus 1, the imaginary number. So if we are using this, the coefficients preserve real values, because only complex values come with odd exponents in Z. So Z to minus 1, Z to minus 3, this becomes complex. But in the half band filters, they are multiplied by 0. The coefficients of the half band filter are 0 in those exponents. So this modulation preserves real valued coefficients. So with this, we get this transfer function. Okay, and now we can design a low pass filter. Then we design a low pass filter. Sorry, I said we can. We have to design a low pass filter called HMA. This low pass filter. Again, if M accomplishes this, we use as cutoff frequencies this one, omega p here, and omega f here. I don't really know how this is called, this letter. I don't know the name of this letter. But okay, these are equations 6C and 6D in the paper. So we can compute them. We know omega L. Here we know m and we know omega l. We can compute it if m fits in that expression. And if m fits in this expression, we change a little bit. We use this. We compute this like this expression. We know omega l. We know m. No problem here. And also we can compute this. We know omega l. So we have to check what is our expression for m. Of course, what we did first is that m has to be an integer. I said m has to be an integer, odd integer. Okay. So after this, we set the ripples of our low-pass filter, but the ripples are not known. This is the ripple delta P and this is the ripple delta S. So we have to specify both with this expression, and delta G is this one, the VD is this one, but again we don't know omega L. So let's assume that we know it. These are equations 11b and 11c in the paper. So let us assume that we know omega L. Okay, we can keep going. We will see these assumptions later. So to design the low-pass filter, we use delta P, delta S, and these are two letters that I don't know, and I don't know the name. But okay, so with those we can compute a proper length for that filter. Okay, but we don't know this one because they depend on omega L. So let us assume that we know the length of that filter. If we know the length of that filter, we can use the Parks-McQuillan algorithm for low-pass FIR filter design, and we can design that filter. So from that filter we obtain two other filters, B of C and C of C. Let's see, B of C is obtained using this equation, which is equation 8 in the paper. So here we have HMA of n. All this is n, the number of the coefficients. So HMA, MA represents that is a coefficient from this filter. So the time index is n. So all of this is n. Okay, so we have to use these coefficients. So B of Z is computed like this. LMA here, and here are this LMA is the length of the low-pass filter, which we assume to know in the step before, the length of this filter. Okay, so this is equation 8 in the paper. So we also obtain C of Z from HM in a similar way. These are the coefficients, HMA of n. These are the coefficients. This is n. This is n. The argument, the number of the coefficient, and this is the length of the filter. Here there was a typographic error, a typo, that it was with a capital M, but it should be a little m. So HMA is the same as HMA. It was a typo in the paper. So this is equation 9 of the paper. Finally, we obtain GA of Z, the second basic filter of the subfilter, the second one. We obtain it from B of Z using this relation, which is equation 4 in the paper. So using this, again we are modulating the filter. Instead, in this polynomial z to minus 1 plus another coefficient by z to minus 2 plus another coefficient multiplied by z to minus 3. So this polynomial, instead of z we replace jz. Instead of z we replace jz, like this. and that is what is meant with this notation here. We are modulating that filter. Here we have M that we already know. Here we have the length that we assume to know. We will see later. And now with this relation we find GA, and then we find then we find GM. We obtain GM from Z of Z using this relation, which is equation 5 in the paper. So with equation 5 we find this relation. Here again we are using modulating Z of Z, replacing every Z in the polynomial. This is a polynomial. Z of Z is a polynomial. So in every expression we replace Z by JZ. J is the root of -1. So we do that, and we find this expression. We find, sorry, this filter. So LMA is the length that we assume to know, the assumption 3. So the design of the 3 basic filters that compose the subfilter occurs in the steps 3, step 7, and step 8. So in step 3 we designed this one, in step 7 we found this one, and in step 8 we found this one. Okay, so up to here I am explaining the FRM applied to the subfilter. This is FRM. There is a routine in alternatively you can use a routine, the code in 1 in this reference. You can use that code. This reference is open access. You can use that code, page 467, to design a filter with that characteristic. In that case, you will use this as a cutoff frequency and this ripple as the desired ripple of this Hilbert transform. You will use this and this. This is given here or given here. So again, we cannot compute this one yet because we are assumed to know a parameter called omega L, big omega, capital omega. So we don't know it, but you have a routine for this. This is in code here. I explained this in steps because in these steps I am going back a little bit. Those steps are presented in the paper because in that time I did not have this chapter. This chapter didn't exist in that time, so it was published kind of in the same days or so. So you can find the code in this to design an FRM based Hilbert transform with those characteristics. Okay, you must be aware that the delay in the 2 branches of the subfilter must be equal to preserve a linear phase. If they are not equal, you have to insert delay elements accordingly to make the 2 delays equal. So that the details are in this reference. Okay, so another thing is that after designing the filter, all the coefficients, or in other words, the filter has to have again a VD. It must be multiplied by VD. VD is given here as let me go here. This is VD. Again, we need to know omega L. We will see later this, but you have to multiply by VD the overall filter. The designed filter will have 1 here, and it will be a delta here, a delta subfilter. I call it delta subfilter, and a delta subfilter. It will be +1 plus delta and 1 minus delta. But we need to give a gain by D to the subfilter so that the peak doesn't surpasses 1, the peak must be at 1 or less than 1. If it is higher than 1, it might introduce undesired passband deviations in the overall design. So that's why we have to multiply the filter, or we have to make it with a gain of VD. Okay, VD. Okay, so that is what I have to say with this filter. After we design it, two things: the delay and the gain. Okay, and then we have to design the prototype filter P of Z. This is a type 4 Hilbert transform. Its specifications are like this. This is the axis, the omega axis. Here the frequency axis is a capital omega, and here omega L is a specification for that filter. Again, let us assume that we know it. We will see later. Let us assume that we know, and this delta is from the specification of our desired filter. Let me go back a little bit, and this is this delta here. Sorry, this delta here. We already know that is our specification. So with these two parameters we design P of Z. This represents equation 10 in the paper. This is equation 10 in the paper. Okay, for now let us assume that we already know omega L to design this filter, and that we have a proper length for that filter. This is assumption 4, that we have a proper length for that filter. We could estimate a length. Sorry for my English. We could estimate a length for that filter using delta and using omega L, but we don't know omega L. So we are assuming that we can estimate. If we have that, we can employ the code in page 453 to design that Hilbert transform in this reference. And the coefficients alpha are derived from the coefficients of this filter through Chebyshev polynomials. And in this case, the relation is not so complicated, but is well explained in this chapter. Also, the code in page 475 in this chapter is includes the complete design with a frequency transformation based Hilbert transform. And so there is the relation. You can see also in the code this relation, how to get from these coefficients to these coefficients in that code. So with that, we have the complete design. What about the assumptions? The assumption 1 was that we know omega L. Assumption 2 is that we know a length for H, the half band filter. But this length can be estimated from the cutoff frequencies, which are known, and from the ripple, which is not known because it depends on omega L. So essentially, if we know this, we can estimate, if we know omega L, we can know the ripple, and with the ripple, we can estimate a length for this. Essentially, assumption 2 is we know omega L. The third one, we know a length for HMA, for the low pass filter. That was assumption 3. We know a length for the low pass filter. This length again can be estimated with the cutoff frequencies, which we know, and from the ripple, which we don't know because we don't know omega L. Essentially, assumption 3 is we know omega L. And assumption 4 was we know a length for P of Z. Again, we know the ripple, it was from the specification, but we don't know omega L, so we cannot estimate a length for that filter. So if essentially assumption 4 is also we know omega L. In other words, if we know omega L, we can know the length of all the filters. In advance, we can estimate the length of those filters. So we need to know omega L. Right in the beginning, let me go back a little bit. Right in the beginning, here, this is the beginning. Right in the second step, here, in this part, when we are specifying the ripple of the half-band filter, we need omega L, and from this point on, we need omega L. So, what can we do to know omega L? Sorry, we go here. We have two options. We can make a guess on it. We can use, for example, omega L equal to 0.5 pi, or we can define a cost function. Let me go a little bit in this part. Omega L is related like this. If omega L increases, the complexity of P of Z decreases, but the complexity of G of Z increases. If omega L decreases, the complexity of P of Z increases, and the complexity of G of Z decreases. So omega L somehow must be in the middle, but it will be nice to find a proper way, a proper omega L that expresses an optimal position regarding to a cost function. But essentially, this is the relation. If omega L gets closer to pi, for example 0.6 pi or 0.7 pi, this filter P of Z gets very simple, but this is a little bit more stringent in its specifications, so the complexity of this increases. On the contrary, if omega L gets decreased, for example 0.1 or 0.05, the complexity of P of Z increases. We have more coefficients, more alpha coefficients, but this gets simpler. So there is an optimal position for omega L. So we can make a guess and start our design with omega L 0.5 or 0.4, or playing with that. Or we can define a cost function for the overall design using the estimated length of the filters. All the lengths depend on omega L, so we can define a function, and we can present a minimizer omega L asterisk. This minimizer would be derived from formulas that estimate the length of the filters using embedded omega L in the corresponding places. This approach is followed in the paper, specifically in equation 14 and 15, A to C. So in those equations is mentioned a cost function. Equation 14 is an estimation of the length of a Hilbert transformer, and equations 15A to 15C is a formula to estimate the length of a low-pass filter. And with those formulas, we can find a cost function estimating in advance the length of the filters. In literature, this one was derived from this one. This one was first, and then this one. Particularly, I found that equation 14 is not exact for big ripples, and the soft filter has big ripples, so the complete formulation gets a little bit polarized, I don't know, biased, gets a little bit biased because the formula is not too exact. To solve that issue, I proposed a more exact formula, which is given in this reference. So That's it. You can use those codes in those in this reference. The basic codes are here. The basic codes are here to embed FRM into FT. Frequency response masking into frequency transformation. You can use the codes here following these steps, and here you can use a proper you can find a more proper formula than the one given in page given as equation 14 in the paper. The one given here is a little bit more exact if you want to define a cost function. And also I recommend to go through this chapter. There are several routines and the explanation of the relation between a half-band filter and a Hilbert transformer, and also the corresponding codes for the frequency response masking alone and for the frequency transformation alone. You can go through those methods, and then the combination is like I explained it in this presentation. So that's it. Thank you very much. See you.